Welcome back to EEG Tutor, Lecture 2, the technical aspects of EEG. I'm your EEG tutor, Dr. J. Hayes McKay. Thanks for coming back for Lecture 2. This lecture will continue to build upon the foundation you established during Lecture 1. Keep trusting the process, guys. This lecture will allow you to orient yourselves to what you're actually seeing on the EEG. This will really pay off down the line when you see more complex recordings. All right, without any further ado, let's get to it. Here's an overview of the topics we'll cover during Lecture 2. Some highlights include electrode naming, EEG montages, the different EEG waveform frequencies and the Greek letters which denote them, and also some really easily confused conventions which I'll go through in depth with you regarding negative versus positive deflections, as well as polarity. During the last lecture, we spoke about how electrodes work. Now let's talk a bit about how they are named. It's actually quite simple. They are named according to the approximate region of the brain which they are recording. For example, FP is frontopolar, F is frontal, T is for temporal, P is parietal, and O is for occipital. Odd numbers mean the electrodes are recording the left hemisphere, and even numbers record the right hemisphere. Also, Z denotes central. So CZ would be dead center in the middle of the head, as you may see here on this diagram. However, also the lower the number, the more interior the electrode. You see here T3 is more interior than T5. That's worth remembering. And then another important exception to mention is that F7 and F8 actually are considered frontotemporal or anterior temporal, despite having an F. You might think this is kind of posterior frontal, but actually it's more frontotemporal or anterior temporal. Now that you understand how EEG electrodes are labeled, let's delve a bit more into how they are arranged or placed on the scalp, as this plays a big understanding in EEG. The 10-20 system is by far and away the most common system of electrode placement. The International 10-20 system indicates the percentages of the scalp covered by electrode distances relative to the nasion and the inion. You see this here where there's the nasion, and you take 10% from this to get to FP1, and then it goes 20%, 20%, and now you're at the vertex, and then 20% to PZ, and 20% back to O1, and then 10% back to the inion. This is why it's called the 10-20 system. It's also referred to as the International 10-20 system. So this is a good perspective when you're looking at the head from the side. However, if you're looking from the top down at the scalp, you might see it this way, where if you have the nasion here, it would be 10% here to FP1, then 20% to F7, and then 20% more to T3, and then 20% to T5, 20% to O1, and then 10% to the inion. Now this obviously changes in terms of the exact distances depending on the circumference of a given head. That's why percentages are utilized, is because otherwise the scalp circumference would be too different on each person to have a standardized system. Just keep this in the back of your minds. This is the standard way electrodes are placed. There are some other systems used, particularly with high density electrode arrays, but this is by far and away the most common. So now let's talk about montages. Montages refer to how we compare voltages between electrode pairs and how we arrange them on the computer screen. Different montages arrange these electrodes differently to show us different aspects of the recording. The most common montages by far are the anterior to posterior bipolar montages, which is the typical screening montage when you're reading an EEG. In this type of montage, each electrode is compared to a nearby electrode. Referential montages, all of the electrodes in one hemisphere are individually compared to a single reference electrode. I'll show you some diagrams of what that visually looks like. An AP bipolar montage looks like this. Sometimes people call it a double banana montage, and you might see why when looking at this diagram here. It has a banana-like shape. These arrows are representing how one electrode is compared to the next. So you see here the temporal chain in an AP bipolar montage is FP1 compared to F7, F7 compared to T3, T3 compared to T5, and T5 compared to O1. The parasagittal chain is FP1 compared to F3, F3 compared to C3, C3 compared to P3, and P3 compared to O1. The central chain is FZ compared to CZ compared to PZ. This is a very, very typical montage you're going to see a lot of. I'll show you some actual screenshots of this type of montage in terms of the raw EEG data later in this lecture. Referential montages look at the EEG differently than AP bipolar montages. In a referential montage, instead of comparing one electrode to the nearby electrode, you actually compare all the electrodes to a reference electrode. This may be all the electrodes in one hemisphere to an electrode that's a reference, or actually sometimes all the electrodes to a single center electrode that is a reference. Nonetheless, this allows you to see the EEG in a different way than the AP bipolar montage. In a referential montage, the area where a waveform is most predominant is actually seen by looking for the electrode with the highest voltage compared to the reference in the chain. We'll touch base on this more later in future lectures, but this is an important concept to at least understand how these montages differ at this time. When you first start looking at an EEG, of course you want to know what montage it's in, but also you want to check the settings. The settings can drastically influence how an EEG looks. There are some common normal settings worth covering at this time. Filtering is often set as a low frequency filter at 1 Hz and high frequency filter at 70 Hz. We'll delve into more about what filtering actually means later during this lecture. Sensitivity is typically set at 7 microvolts per millimeter. When you go to a lower number, so say 5 microvolts per millimeter, this actually increases the size of the waveforms. Okay, so because that means there's a smaller area of voltage that's given the same amount of millimeters, so the overall size increases when you do that. With regard to the time base, 30 millimeters per second is the normal time base. Sort of similar to the sensitivity where when you go down in the number, it actually gets bigger. It's kind of similar in time base. So when you go down in the number, you're actually now compressing the recording. So you're seeing more seconds on the same screen size. So with 15 millimeters per second, you're actually seeing twice as much of the recording on the same screen size. I'll go through this more with you when we actually look at EEGs, but just understand these basic settings for now and just try to kind of commit these to memory as you look at several EEGs and just get a sense of the normal settings now to have something to reference back to. So if you're looking at the EEG settings above here, you see the low frequency filter is at 1 Hz, like we said it should be, in a normal kind of setting. The high frequency filter is 70 Hz. One thing we didn't talk about is the notch filter. This takes out a specific frequency band from the recording. AC current has a lot of 60 Hz artifacts, so it's common in the US to have a notch filter set at 60 Hz. With DC current, it's commonly set at 50 Hz in some international areas that use that standard. We talked about the sensitivity. Do you see anything off here compared to the normal settings we just previously discussed? Well, here we have 10 microvolts per millimeter, whereas we said typically the normal is 7 microvolts per millimeter. That's okay. You often have to change the sensitivity based on kind of how high of amplitude someone's waveforms are at baseline to just normalize how it looks on the screen. But it's worth noting when you've changed the sensitivity from normal settings. The time base here is at a normal 30 millimeters per second. It's worth pointing out in the recording here that each one of these blocks between these denser lines here is 1 second. And then each one of these lighter color lines divides it up into fifths. This is a point of reference for you to kind of see, hey, what's the frequency here? Because the frequency is the amount of cycles per second. So it's the amount of cycles per one of these distances here. The signal chain in a recording is typically set up like this. You have the pyramid neurons, again, from the biophysics lecture, creating electric dipoles which summate, and then an electrode records them. This signal is amplified and then filtered somewhat with analog filters before it's processed by an AD converter. An AD converter is an analog to digital converter. This allows us to convert the analog data to digital data, which we can view and manipulate on a computer. I want to briefly review how filters work during this lecture. These models for filtering are old school analog filters, and while digital filtering is done differently, this does give us a good conceptual model to understand what is happening when we filter a signal. Filters do have the ability to radically change how the signal appears to the EEG reader. Low frequency filters work by sending the signal through capacitors. Capacitors block low frequencies more than high frequencies. So this allows the high frequencies to pass through. Therefore, low frequency filters are sometimes called high pass frequencies as well. The formula to the left here is the impedance of a capacitor. So the higher the frequency is, the less opposition to current flow there is. This is why the higher frequencies pass through more so than the lower frequencies. This is a logarithmic representation of this, where you see that the high frequencies are being passed through at a much higher gain than the lower frequencies. High frequency filters are in most ways the opposite of low frequency filters. The signal chain is actually almost the reverse too. Before we had the capacitor here and then a resistor down here before the ground. Now this has been reversed. So what happens is that the low and high frequencies come through this resistor, but now they have to make a choice. Do they go to the output or do they go through this capacitor to the ground? Well, the higher frequencies gladly pass through this capacitor and go to the ground. The low frequencies, however, do not make it through a capacitor as well and end up being shunted to the output. So this is why you have more of the low frequencies making it through to the output. This is called a low pass filter alternatively. I like using the term high frequency filter because it just is a more direct way of stating what it actually does. It's less confusing. Again, here's a logarithmic representation of what this actually means. It's the reverse, more or less, of the low frequency filter. And here you see that the gain begins to drop when the frequency gets higher. So it's not passing through as much gain of these higher frequencies. Resistance is really kind of equivalent to this impedance of the high frequency filter. So just kind of store that away in case that formula comes up. It's a simplified formula, but sometimes you'll see that. So now we get to an important topic to just be able to talk about EEG with other readers. Different frequency bands have different Greek letter designations. Hertz is the number of cycles per second, like I previously mentioned. Each little segment on the EEG that is 1 second has a number of cycles of a waveform. And this can be either delta, theta, alpha, or beta, depending on how fast the waveform is cycling. When a waveform is less than 4 hertz, it's considered a delta frequency. 4 to 8 hertz is considered a theta frequency. 8 to 13 hertz is considered an alpha frequency. And that is true even if it is 8 hertz. You might wonder if it's 8 hertz, is it a theta frequency or an alpha frequency? Well, it's an alpha frequency if it's anywhere from 8 to 13 hertz. If it's greater than 13 hertz, the frequency becomes a beta frequency. What type of frequency do you think this is here in this box here? If this is 1 second, how many cycles do you see? If you thought it was an alpha frequency, you'd be correct. How about this one? It's a lot slower, right? Well, this is a delta frequency. You see 1 cycle, then 2 cycles per second here. There are some intermixed alpha frequencies that are lower amplitude, but the predominant frequency here is delta. Okay, we've reached perhaps the most confusing part of this lecture. However, I hope to simplify it down for you. There's a convention in EEG designating which is a positive or a negative deflection. This is referring to whether the waveform goes up or down when one electrode is compared to another in an electrode pair. By convention, it is a positive deflection if the first electrode of the two being compared is more positive than the second. This results in a waveform that goes downward. That's what throws people off, because you might more intuitively assume that a positive deflection goes upward. However, it actually goes downward. So there are two ways I've found that are most helpful to remember this. The first is a system I developed myself to help me visually remember better what was going on. So what I did was I put two relative charges, one representing E1 or electrode 1, one representing E2, on a Cartesian coordinate system here. And how I think of it is this, is if the electrode 1 is more relatively positive than E2, then this is a positive deflection named after the first electrode being more positive than the second, but that the direction goes down as if this was a weight system, like a pulley weight system on a Cartesian coordinate system that would be pointing down, because the E1 would be positive and E2 would be negative, and that would cause it to point down, and that's exactly how it would deflect. This conceptually helped me remember it much easier, and once I put this together mentally, I never forgot this convention. One other simpler way that's more just kind of rote memorization is to think of it as the deflection is named after the first electrode in the pair, and then it goes in the direction more intuitively of the second. However, I like this model better because when you start to get confused, you can visually think back to it. A negative deflection would be the opposite. So if E1 is more negative than E2, then this orb drops down in this Cartesian coordinate system, and then the second electrode point is up, and that makes the arrow point up, or this is pointing upward. And that's what you see on the EEG, is the waveform actually deflects upward. I hope you have this concept down. If not, rewind a little bit and watch this again and just kind of commit this model to your memory the best you can. This really did help me just keep it all straight over time, especially during the first few months that you're really delving into EEG and things can get wonky sometimes in your mind. So just commit this Cartesian coordinate system the best you can to your memory to help you never forget this. Now, there's such a thing as a polarity of a discharge, which is often described more as phase reversals. This can be confusing because it's not the same as a deflection of an individual electrode pair. This relies on you seeing a field. So if you say there's a positive polarity discharge, that means you see a field that creates something that looks like this, that you could put a plus sign in between. And a negative phase reversal or negative polarity discharge would create something like this, where the two waveforms come together, and that you can slide a little negative symbol in between them, but not a positive. So this is important to remember. So, this would be the first part of this waveform here is a positive deflection, and then the second part is a negative deflection. But together, actually, the polarity is a negative polarity of this discharge. It causes these to come together like this. And I'll show you why this is on the next slide with a more of a 3D model of this. But just realize phase reversals and polarity are different than electrode convention for as far as deflections go. Okay, so if you have a negative discharge here at E2, around E2, and you have three electrodes you're looking at here, E1 compared to E2, and E2 compared to E3. Well, so the first deflection here is E1 compared to E2. This is going to be what, a positive or a negative deflection? Well, it's a positive one, right? Because E1 is more positive than E2, so we go back to this Cartesian model. That means E1 is here and E2 is here, and that causes the arrow to point down. Then you have the next electrode pair we're looking at, which is E2 compared to E3. Is this a negative or a positive deflection? Well, this one is a negative deflection. And that's because E2 is more negative than E3. So again, in this Cartesian system, that drops the negative orb down and the positive second electrode orb up, and that points the arrow up. So this Cartesian system here creates a waveform that looks like this, and this one here creates a waveform that looks like this. And so overall, this discharge here has a negative polarity, and you see a negative phase reversal here. You could slide a negative symbol right in between these two. Okay, now here's the opposite. Here we have E1 is more negative compared to this big positive discharge here at E2. So what's this deflection when we compare E1 to E2? Is it negative or a positive deflection? Well, it's a negative deflection, right? Because even though E2 is really, really positive, E1 is more relatively negative than E2. So you get the same kind of thing we looked at before, where you put this orb, the E1 is negative and E2 is positive, and the visual representation means this is pointing upwards. Or you can just remember the second electrode is more positive, so it's going to go up, even though it's named after the first. Then you see the opposite of this when you look at E2 versus E3. This is, again, a positive deflection, and you see that it's going to kind of point down in this system, and that's what it looks like when you put these two together here. Is it called a positive polarity discharge here, where you can see you could put a nice plus sign in between this negative deflection and the positive deflection here. When you see the field of it, it has a positive polarity. All right, guys, you know what time it is. It's question time. Let's review some fundamental concepts that we just covered. Question 1. What is the most common system used for electrode distance spacing? Is it the International 1020 system, the WHO 1015 system, or the International 1015 system? If you answered the International 1020 system, you'd be correct. Question 2. In which montage system is the maximum amplitude the area that is the highest voltage? If you recall back, we covered a couple of different montage systems. Would you say this would be the transverse montage, the referential montage, or the AP bipolar? If you answered the referential montage, you'd be correct. Again, the referential montage compares a lot of electrodes to a reference electrode. And you look for the electrode that's compared to the reference with the highest amplitude to say, hey, this is the point of maximum voltage. Okay, question 3. What is the frequency band highlighted below? If you're looking down here at this box here, you see a certain number of frequencies in here. Would you say this is going to lie in the delta range, the theta range, the alpha range, or the beta range? If you thought it would be in the alpha range, you'd be correct. Recall again that the delta frequencies are less than 4 hertz, theta is between 4 and 8 hertz, and alpha is 8 to 13 hertz, and beta is greater than 13 hertz. Okay, question 4. If the first electrode is more positive than the second electrode, meaning it's a positive deflection, which direction will the deflection physically go on the EEG recording? Would it be downward, upward, or isoelectric, meaning flat? If you answered downward, you'd be correct. Let's review that Cartesian system I taught you guys. Remember that if the first electrode is more positive than the second, you have this dumbbell system where it would point downward, and that would mean that the overall deflection would actually go downward on the EEG recording. Question 5. Which of the below waveforms represents a discharge that is positive polarity? Think about that for a second. Remember that polarity is different than if it's a positive deflection. Polarity relies on field. If you answered B, you would be correct. Remember, with positive polarity, you can actually fit a little plus sign between these waveforms which are opposing. Whereas here, you actually have a negative polarity discharge at A, and you can fit a little minus sign in there. Here are some references utilized. These were the same as Lecture 1. All right, congratulations. You've made it through Lecture 2, the technical aspects of EEG. You've now established the appropriate foundation to build upon as we see normal awake EEG in the next lecture. Thanks for continuing to trust the process. I'll see you next lecture. I'm your EEG tutor, Dr. Jake Hayes McKay.